Okay, good morning. So I hope you have been doing the exercises that I have given to you last time. I think those exercises in fixed, prefix, and postfix. Right. So I have discussed on trees yesterday for the data science classes. So I think today we will start trees for you, cybersecurity. So we have a lot of time today. So there are two periods for our lab and one period extra. So we will cover up all the theory. I have uploaded this PDF already to you, which looks like a PPT. This is enough for your theory exams because most of the concepts have been covered in this. And today we will talk about some aspects of trees in a theoretical perspective, along with it, and some mathematical perspective. And we will go for binary search tree, how to construct a binary search tree, and then we will discuss on how to write a code for a binary search tree. Okay, and for that you should be having some knowledge on recursion. That's a prerequisite, because as I said, trees are not linear, they are non-linear. You cannot use a while and for loop that easily that you have used in linked list. So it is better for us to have a recursive type of solution. We will discuss all the solutions. If there is looping solution, then fine. If there is a recursion solution, that's also fine. Okay. So coming to the concept, I think because I have explained yesterday, I don't. I thought that it is not saved, but the complete red ink which I have drawn yesterday was there and it is saved in the PDF. So it is better for me to download a new one, I think. So otherwise you will get confused. Let me download a new one from your learn. I think you can also download it because I have uploaded that one already. Just a second, I will get it now. I have written a new unit
Alert
called
from
trees.
your disk is almost full.
You can see that unit in that. Okay. Now I got it into the downloads. Right. Okay. So now I'll share the screen and we will go. Right. So, to the definition of trees, a tree is considered as a finite set of one or more nodes. So, a tree also looks like, what we say, just a second. Okay. So, a tree also looks like the linked list, but it is not the linked list. It also is a finite set of one or more nodes, such that there is a specially designated node called root. Of course, in our linked list also we have a node called root, right? This first node is always called a root, and it continues till the last node. So Hello?
Alert
Yes,
from your
Hello?
yes, sir. You're audible now, sir.
Okay, okay, fine. My internet is completely unstable. I don't know why. If there is any disturbance, please tell me.
Yes, sir.
Okay, right. So if there is some disturbance, I will also post the video yesterday's because it is very fine that we discuss it continuously without any disturbance. Okay, coming to this. So can I proceed? Is it okay?
Yes, sir. It's okay,
Yes,
sir.
sir.
Yes, sir.
Right. So, we have a linear thing. So according to the linear, we discussed that it is sequential, but non-linear is not sequential. So linked lists are sequential, so linear, but trees are non-linear, so they are not sequential because the tree structure might be different. It might contain this thing, and so on. So this is how the trees will exist generally. So this comes under your class structure. It looks like your class and your subclasses. You see here, if there is an animal, if there is a directory called animal, so trees real-time application is your file system. Have you seen or not, even in your CMD, I don't know, present Windows systems are enabling this tree structure or not, there is a command for viewing trees. That means, for example, if there is a folder called animal and there are subfolders like this, maybe dog and cat. Okay, so in this again it will divide into again subfolder. So the dog is divided into another subfolder, the cat is divided into subfolders like breed 1, breed 2, and so on. So when I started using Windows, I stopped using Windows at Windows 7 itself. I never used 8 also because by the time 8 came, I shifted to Mac. So I don't know how 8 is working properly. But up to 7, I can see that there is a side window when you consider your complete window of your folder or a drive. See, all the folders and files will be here. The complete list of desktop, my computer will be here. And in this, you can see the tree structure of how it is actually located, the entire folder. So when you click on the folder, it will help you to see what are the files and folders that are there. Not only this one, I think you can see this tree structure in your editors also. When you write a code, you can see that when you are doing a project, in that project, how many folders are there, and in each folder, what are the files that are there. You will have that plus minus symbols also, right? If you want to expand, it can expand. So the basic application of a queues that we have already done as a project. I don't know how many of you are ready with the project. At any time and any day, I will just upload and remove it within few hours. So you have to upload your project for that micro project queues. I think you are ready with it. So what is the real-time application of the queue that we have seen is processing the processes or the programs one by the operating system in a queue structure. The real-time application of a stack program is something like we use that main function calling another, and even in the recursions, we use that stack type of concept. And trees are basically used for storing the data in such a way that they are all related with each other in a hierarchical representation, most probably. because, and that is the reason why they have a real-time application called the file system. Now see this one. If I have a directory or a file called, so this is called directory. I have this directory and it has some files. This is one file called dog, not file, that's a folder. This is called cat, and this is called cow, something. And in this dog, you have again the La Chapsa, the Labrador, or Alsatian, something, German Shepherd or something, and cat. I don't know this cat and cows. Okay, I'm interested in dogs, so I know these breeds. Okay, now you have the. This is the hierarchical structure of your entire folders. In an animal directory, you have dog directory. In that, you have ls, lb, and a directories. And in each directory, you are storing the photos of different dogs of the same breed. These are all files, maybe of JPEG and so on and so. And you can see what is the root of this entire tree structure? Can you tell me? Anybody can tell me this one?
Animal, sir.
Animals.
Right. So now you have to say that the entire tree structure is having a root animal. And you have substructures. This is one subtree, this is another subtree, and this is another subtree. For each subtree, you have to consider that dog is itself the root of this subtree, because this is one subtree, right? Again, for this one, ls is the root of this subtree. So it's like subtree in a tree and subtree in a subtree. So this is the entire tree, right? This is the entire tree, and this one is the entire subtree, and this one again is the subtree. So according to data structures, the hierarchical representation is generally considered as the trees itself, because it starts with one and ends up with many. So they are all called the leaf nodes. Why we say it's a tree? Because we start with a single seed and a root, right? From that, the tree comes and expands into different branches. That's how it actually happens. If you just inverse it, so we have a seed and root here, and from this your tree is expanding into different branches. If you inverse, it looks like a tree. That's the reason why it is called a tree with a root. Now let us look into the definition. A tree is a finite set of one or more nodes. You might ask me what is a node. I will tell you in the next slide. So nodes are those animals, the directories that we consider. Okay, that's the real-time application. But if you want to store the numbers, so generally in our examples we go with numbers only, not this real-time applications.
Sir.
Just excuse me for a moment. Okay, I'm using the college net, and that is the reason why I'm getting these much of disturbance. My phone charge is also over. Excuse me for this. Okay, I will tell you the reason why we have this condition. So have you seen that in stacks and queues, we have discussed with numbers. right? We used to do it with numbers only, 5, 6, 7, and so on, so with top and all. This is a demo part of explaining the concept. So in trees also we do the same thing. In trees also we have the same explanation of how you arrange the trees like this. So there are two types of notations that I use generally. This is the way I use it. Okay. Now am I audible, right? Can I proceed? Any
Yes, sir.
problem?
Yes, sir, you
Yes,
can.
sir.
So you have these nodes. So these are called nodes. In our stacks and queues, we call them as elements. And in our linked list, we call them as nodes, right? So by this time, you might understand that the trees are also having a connection with the linked list. The reason is, in a linked list, we call them a node, not an element, because it consists of two parts. One is an element and the other one is address. Even in a double linked list also, it consists of two parts, element, the previous address and the next address. So that is the reason as a whole it is called a node. And by this time you might have understood what is the structure of a node in a tree, right? Because there is a connection and a link between different nodes. So it is a finite set of nodes with a root. So root is very important here. And the remaining nodes are partitioned into n greater than equal to 0 disjoint sets. So that means your end, if you are saying that there are some sets of nodes, you cannot say that it n should be less than or equal to 0. Because if it is 0, how can you say it's a tree? So always it's greater than 0. At least you should have one of tree. Now I will explain you what exactly this means. I will explain here itself. If you have a root like this, right? If this is a root and you are considering connecting another node to this, and this node is having a connection with other node, and this connection with other node. Now you need to understand that this is root. This is subtree, right? And you see, this is one disjoint set. This is one disjoint set. Okay. And if you have another connection having this node, and this one is divided into two parts. Again, there are two nodes here. This is one connected and this is one connected like this. And you see here, this is another disjoint. So that means if you consider these many disjoint sets, so I will tell you here itself with an example. See, in the previous example, I want to say that a dog is subtree 1, cat is subtree 2, cow is subtree 3. This is root. So it is a finite set of nodes consisting of root and T1 to Tn disjoint sets. That means each subtree is not connected to the other. Do you find any connection between dog and cat?
No,
No,
sir.
right?
No, sir.
You cannot find any connection with dog and cat and cow. So these are disjoint. Animal is connected to dog, cat is connected to animal, and cow is connected to animal. So animal is having a connection with dog, cat, and cow, but there is no connection between dog and cat. So they're all disjoint sets. That's what the meaning itself says. And you can see the last point. We call the T1 to Tn as subtrees of the root. That's what your dog, cat, and cow. Okay, right. So that is the meaning of your tree. So if anybody asks you the definition of a tree, you can say it is a finite set of one or more nodes. Why? Because one, we are saying at least your tree has a root. You see that plants, when you just put a seed in the soil, that means you are expecting a tree there. So at least if a root, a small seed and a root is there, that itself is a tree. The tree is slowly starting from that. So at least if you have a root node, then we can say it is a tree. The remaining nodes are partitioned into, if there are any remaining nodes, then the n nodes should be always greater than or equal to 0. Okay, it should not be less than 0. That's a simple condition, we know that. Either if you want to keep the number of nodes, if there is only one root, that means there are 0 subtrees, so n is equal to 0. If there is a root and there are some subtrees, then n is greater than 0, right? So you can consider when n is greater than or equal to 0, there might be T1 to Tn disjoint sets, and each set is called a subtree. That's what the entire meaning says. Okay? Yes. Now we talk about the terminology of the tree. See this particular condition. The entire scenario is given like A is connected to B, C, D, E, F, G, H, I, J, K, L, M. Now I will ask you few questions. How many subtrees are there in this tree? Hello?
Sorry, the
10,
three.
sir. 10, sir.
How many subtrees are there in a tree? You should consider only the first row that is connected to the first level that is connected to the root. Now tell me how many subtrees are there?
3, sir.
So
3.
three, sir. Three, sir.
Yes. So there are 3 subtrees for a tree which is having a root called A. The subtree 1, subtree 2, and subtree 3, which is B, C, and D. Right? Now, from 1 to 3, they are called nodes. They are called nodes. Then you might ask me why K, L, M are not considered as nodes. I will tell you why. K, L, M are the last level and they are not at all expanded anymore, and hence they are called leaves. They are called a leaf. So in a tree, you will have the end of the tree is with a leaf, right? When a leaf comes, there is no expansion to that. But what are the nodes? A node that can be expanded to the next level. So if K is expanded, then K, L, M are considered nodes, and whatever that is expanded will be considered as leaf itself. Did you understand? Okay, so let us go with this one. So what is a node? This is a node, this is a node, this is a node, this is a node, and this is a node, because you have expansion to the next level. If E is having KL, there might be a probability that F, G, I, J should also be having the next levels. But after this level, there is no another level that is coming. Hence, these are called leaves. They are not called nodes. Technically, they are also nodes, but according to the concept, these are called a leaf because they are the end of the tree. Okay. Now, consider the degree of a node. The degree of a node is told as how many branches are divided from it. So if you consider the degree of a node A, it is 3. You see here, the reason B, C, D are divided. Now can you tell me what is the degree of node C?
One, sir.
1,
One, sir.
because from C, yes, tell me. Okay, from C you have only G. What is the degree of node D?
Three, sir.
3,
3.
sir.
From D, you have H, I, and J. The degree of node B is E and F. The degree of node E is K and L. The F degree is 0, G degree is 0, for H it is 1, and so on. So the degree of a node is defined as how many children the node is having. Leaf. Now I will tell you one thing. F, G, I, J are also considered leaves, but they are called leaf node. The reason is they are not simply leaves because they might be also turned into nodes, but they have no nodes at present, and hence they are the end of that family of F, and hence they can be called as leaf nodes. So we have two things: leaves, terminal and non-terminal. So I can say something like this. At this, you might expand it and you are terminating here. Okay, these are the terminal leaves we can consider. Somewhat we can have non-terminal leaves also. That you have to understand. So most probably all the nodes which are not having any nodes below that are always called the leaf nodes. And remaining nodes which are having children are called the nodes themselves. Considering the parent and the children, the same class concept. A is the parent of, okay, A is the parent of B, C and D. Here B is a children, C is a child, D is a child. If you consider E and F, B is the parent of E and F, C is a parent of G, and D is a parent of H, I, J, and so and so. Now tell me who are siblings here?
E, C, and D
E
are
and F, sir.
sir.
So in our consideration, B, C, and D are the siblings. E, F, G, H, and so are the siblings in the next level. So I consider most probably B, C, D are the direct siblings. E and F are the direct siblings because they have the common root. So most probably don't say E, F, G, H, I, J are all siblings. You have to say E and F is one sibling. G is one. G has no siblings, of course. H, I, J are one sibling, and K and L are one sibling. So that is what the sibling. So sibling is defined as having the common root. So E and F having B, so E and F are considered siblings. Now what is the degree of a tree? Until now we have seen the degree of the node is individually we are calculating. What is the degree of the tree? Can you tell me? Just imagine and tell me.
The branches of root, sir. Number of branches of root.
Number of level minus 1, sir.
Yes. So a tree has a root called A. So somebody please switch off the mic. A tree has a root called A, and hence the degree of this tree with a root A is having the three subtrees, and hence the degree of the tree is 3. That's how you need to understand. And remaining all is not at all required, because if you consider this whole thing as a tree, there is a root called A, and for this root you have 3 sub branches or subtrees, and hence the degree of the root of a tree is always the degree of your tree itself. Okay, if you consider this subtree with B as a root, then can you tell me what is the degree of this tree?
2, sir.
2, because from B now E and F. Okay, that's how you need to consider. Now we talk about ancestor. So like our branches, you say always, I will say in Andhra there is a lot of caste feeling and people will fight with each other generally using caste. But I will say all came from a single root. If you consider the DNA and the genes and all scientifically, most probably at least 50%, 20 to 50% is matching with all the people. So just names are different, but you know, in our old inscriptions, if you study history, people all climb to the same type of ancestor, Durjaya or something. They will claim that Durjaya is the ancestor or something. So most probably, almost all the castes in Andhra claim to the same ancestry. So, but the problem is that we are divided into different subtrees. So our entire families are also considered as a tree structure. And we see how B is divided into E and F, K and L. If K is divided into many branches, finally we forget that we all came from the same root called A, because we have many branches in the meanwhile. So that's what our ancestry is considered. Next thing is the level of the node. So the level of the node is something like this. For example, can you tell me at what level E is there?
3, sir.
3, because you can see these items, like if you consider this as I, like we have discussed in the merge sort, right? This is level 1, this is level 2, this is level 3, and this is level 4. So based on the level itself, we can say that the node, so there is a problem called level order traversal. Level order traversal. That means you have to go for each level and find out what are the nodes that are there in each level. Right? That's little bit difficult. That's also challenging, which we will discuss and give it as an assignment. So levels, each node is represented as a level. So E, F, G, H, I, J are in level 3, B, C, D are in level 2, and A is in level 1. So if you consider there is a tree, it should at least have level 1 in it, because it is a root node. Level 1 will always be in with the root node. Can you tell me what is the height of the tree?
4, sir.
4, sir.
The number of levels in a tree is nothing but the height of a tree. So if you just inverse it, how do you consider the height of the tree? Up to leaves you will consider, right? The same thing happens here. So if you take from 1, 2, 3, 4, so you can say the height of the tree is 4. So though the answer is there itself, you can see that by counting this level, this level, this level, and this level, you can say that the height of the tree is 4. So these are the terminology. Remember the terminology. What is a node? The degree of the node, leaf with terminal and non-terminal, parent, children, sibling, and degree of the tree, ancestor, level of the node, height of the node. Okay. Now this is what the slide indicating the terminology, and we have explained everything. Okay. So the degree of the node is the number of subtrees of a node. So the degree of A is 3 and the degree of C is 1. That's what we discussed. The node with degree 0 is the leaf or the terminal node. Okay. Because you can say that's where you are terminating the entire tree. That's why it is called a leaf, which has no nodes beside it. A node that has subtrees is a parent of the root of the subtrees. The roots of these subtrees are the children of the node. Children of the same parent are the siblings. That's what we discussed, right? Like E and F are the siblings of a node called B. The ancestors of the nodes are all nodes along with the path from the root to the node. So for the whole tree, the ancestor is A. For the subtree, the ancestor is B, and so on. So that's what we have discussed in the previous thing, right? You can see here. So ancestor for the whole tree is A. The ancestor for this subtree is B, and the ancestor for this subtree is C, and so on. So right. And you tell me here, it is a representation of a list in a sequential way, actually. This is not very good, but still we can represent this in a sequential way also. Now, if you consider A as a root, can you tell me what are the children that are there? I will mark it.
So B,
Yes, B,
C,
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 D.
and D,
and
sir. D, sir.
these are the children, and hence you can consider this as one subtree. Okay. So that is the reason why the open bracket is there and the whole subtree of B. Next, the whole subtree of C. Next, the whole
Sir,
subtree of D is there, right? And for B, what are the children that you have?
E and F, sir.
E and F, sir.
Yeah, E and F. So these are the children that you have. For C, it is the children, and for D, it is the children, and I and J, and so. So you can represent a tree even in this. So I can use this type of representation for my trees example also. It's very easy for us to represent like this. So when I design the experiment for trees for you to do the exercise, so using code check, I can use this type of format to determine whether it is a tree or not. So when you form a tree and return it to me, it can cover it like this. So I can write a code to make the entire tree like this, and I can compare them as a string. That's how I can do it. So this is one type of representation. So you can say that A is representing the root of B, C, D, and B is representing the root of E and F, and D is representing the root of H, I, J, and C is representing the root of G. Again here, E is representing the root of K, L, and H is representing the root of M, and so on. So, okay. If you just, after the class, if you just look into these slides and if you understand, you will definitely remember what are the things that we have talked now. Okay, this is what we have our representation. So a data will be there. This is the node structure. Data, left child and right child. So now we will discuss on how the structure of a node will be in a tree. Come back to this board. So I think you know what is a double linked list, right? In a double linked list, the representation is with 3 compartments in a node. This is a double linked list. You have your previous address, next address, and an element. The element is nothing but the data. Because the double linked list is sequential, you have a connection to the previous address and you are having your data and your next address. Of course, the last element will always be having your next address as none. We keep using this type of structure for our tree node also. Then we will discuss on how the tree node will be existing. So as I have told you, if this is a tree of these many things, or if this is a tree, any way I can represent, either a circle or something. This is a normal pencil representation on paper, B and C. If this is the case, then how do you understand that for a node, for a small box, how can you connect 2 other boxes like this? And by this time, you know that this is the left side connection and this is the right side connection. So by this time, you should imagine that the node should be having a left address and a right address in between a data. So you have your left address LA, the right address RA. By this, you can connect the left to another left subtree node, right, with again a left address and right address and data, and the right subtree node with left address, data, and right address. That's how you can connect it. So this is a paper representation and this is the memory representation in a computer. I hope you are understanding. So you can create a class of a node with left address, right address, and data on how you have created your node in a double linked list. So in a double linked list, you have created previous address and next address. But here you have left address and right address. This is the small change that you have. And of course, the entire change is how you insert the nodes with one another, how you connect the nodes with one another. It's not equal to the linear double linked list. This non-linear trees are different in connecting the nodes. but the node structure looks alike double linked list. That you have to understand. I think by this time you understand what is the node structure. And that is what it is represented here. You have a data, left child and right child. 1 second. Okay, let's go to the next one. Binary trees. So until now, we considered only trees. Tree is different from the binary tree. A tree can be divided into many number of nodes. So each node can have n number of children, 3 or 4 or n. But when you consider binary trees, so a binary tree can be considered as binary itself. Can anybody tell me what is binary?
More than one, sir.
Is it okay now?
Yes, sir. It's okay now.
Okay, fine. Now tell me what is a binary tree? How do you estimate that it is binary?
Sir, you're not screen sharing, sir.
Uh, I'm screen sharing already.
No, sir. Your screen is not. You're not screen sharing it, sir.
Okay. Now,
Sir.
now is it visible?
Yes, sir. It's visible, sir.
Yeah. Can anybody reply to me? Is it visible now? The
Yes, sir.
screen
It's
share?
Yes, sir, it's visible.
Ah, okay. So now binary trees. We have just discussed on trees until now. But what is binary tree? Any estimation, imagination of binary tree?
normally binary means Making a part into two, no, sir.
Yes, binary means if you have a part like this, you are cutting down into two parts. That's what binary. So when you talk on binary trees, you need to understand that if there is a node that can only have at max of two children, at max of two children. That is what you need to understand. So no more than two. So the number of children should be always less than or equal to 2, and it should be greater than or equal to 0. That you need to remember. The number of children in a binary tree can be at max of 2. So hence there might be no children, or there might be one child or two children. Okay, so it can be either 0 children, one child, or two children. This is what a binary to be having. So this is the structure of binary. So the entire tree will be having only this one child, sorry, one root, and you will have a child maybe like this, and each child again will be having two children. That's all. This is a strict rule for this binary tree. So that's what you are saying. A binary tree is a finite set of nodes that is either empty or consists of root or two disjoint binary trees. Now you see the difference between the trees and the binary tree. So here you can
It's
see
10 o'clock.
that a binary tree is slightly different from the tree. That's what you have to understand. The A is having three subtrees. That means it is connected to three nodes or the three branches B, C, D. But if you consider this one as a binary tree, A should be having either B or C. That means a left subtree and right subtree, B, C. And D should be connected to either C or B. That's all. So D cannot be directly included to A. It's a strict rule. In a binary tree, there should be having only two children at max. There should be no more than two children. అంటే రెండు కంటే ఎక్కువ ఉండకూడదు children అనేవాళ్ళు. It should be at max 2. That's what the binary tree is defined as. You can see the binary tree is a finite set of nodes that is either empty. So children ఉండొచ్చు ఉండకపోవచ్చు. Consists of a root and two disjoint binary trees. Why I'm saying they are disjoint? Can anybody tell me? The left subtree and right subtree.
Sir, because they don't have same child.
Yes, they don't have connection with each other. If this is a root and this is the left subtree LST and right subtree RST, and they are not connected with each other, right? And hence these are two disjoint subtrees. They might be having another few things. This is another LST, this is another RST. If this is considered as a root, and this is one LST and this is RST, which is considered as root. Okay, again this one is like that, again this one. So this entire thing you can see it is not connected to this right side. So these are two disjoint sets. That's what I want to discuss on. Okay. So any tree can be transformed into binary tree by left child and right sibling representation. Okay. Now in this case, this LST and RST are siblings because they are having the same ancestry. These two are siblings because they are having the same ancestry. These two are siblings because they are having same ancestry. These two are siblings because they are having same ancestry. Okay? That's what you are saying. Left child and right sibling representation. But in the previous thing, we said trees are having siblings more than two. It is not a binary tree. But if you have siblings at least maximum two, they are called binary trees. So you can say the left subtree and the right subtree are distinguished. There is a difference between left subtree and right subtree. But every node will have at max 2 nodes. That's what a binary tree representation. That's the difference between the tree and a binary tree. Now you can see it's a representation of a binary tree. Now tell me, what is the degree of A?
1, sir.
1, sir.
What is the degree of B?
2, sir.
2. Because E and C are siblings. What is the degree of E?
2, sir.
2. What is the degree of K?
1, sir.
Sir.
1, right? The degree of 0. And the degree of C is 2. This is 0. This one D is having 1. H is having 2. 0, 1, 0. Now, have you seen at anywhere you have something like more than 2? Is
No,
there
sir.
any number degree than 2? No. And this is hence a binary tree, definitely. Right? This is a binary tree. So, because the maximum degree that you have 2 and the minimum degree that you have is 0, this is a binary tree. The binary tree never crosses the degree more than 2. That you have to remember. Yes. So I will discuss these slides differently because during implementation you will understand what is represented in this slide. So it's all the conditions that we need to see during the representation. That means including all the nodes in a tree. Yeah. The sample of trees. Trees are divided into few types based on their representation. So the right side one is called complete binary tree. I will explain why it is called complete, and the other one is called skewed binary tree. Okay. First of all, we will discuss on few things of the trees of a binary tree. Then we will continue with what is complete binary tree and what is skewed binary tree. And I think by this time you can see that the difference between the skewed binary tree and complete binary tree. Skewed in the sense it is only going towards the left side. Okay. And here it is only going towards right side. Either left completely or the right completely. You see, A's left is B, B's left is C, C's left is D, and D's left is E. So skewed binary tree. And the same way, if everything is right, then it is also called skewed. If a tree having both left and right and this type of representation, then this is called a complete binary tree. I will tell you what is complete binary tree and what is full binary tree. I will tell you that. Now let us go to a small mathematical part. How do you find out in a binary tree how many nodes should be there in a level I? So if I say to you, hey guys, how many nodes should be in level 3? How do you find out? Just we will go for the mathematical representation. For that, let's look into how a tree should be. For example, this is one node. These are one nodes. This is another one. This is another one. Let us see that we have a full binary tree. Only consider the full binary tree, not even complete. Complete is different from full. Okay, this is our binary tree. How many levels are there here? 1, 2, 3, and 4. How many nodes are there in level 2? Tell me.
2,
2,
sir.
sir.
2. How many nodes are there in level 3?
4, sir.
4. How many nodes are there in level 4?
0,
8,
sir.
sir.
8,
Oh,
sir.
0, sir.
8. Right? How many nodes are there in level 1? 1. Now,
Only one.
based on this, can you tell me, because it is binary, we should always consider to be 2 powers, like your med sort, like how we calculated the time complexity. Now tell me what are the things that you do? How you get 1
Two-
with 2 power?
2 power 0, sir.
2 power 0. How you get with 2 power?
2 power
2
1.
power 1.
2 power 1. How you get with 2 power?
2 power 2.
2. And this 2 power?
2
2
power
power
3.
3.
When the level is 1, you are going with power 0. When the level is 2, you are going with power 1. When the level is 3, you are going with power 2. If you consider this level as I, then tell me in terms of I, what is 2 power?
I minus
I
1.
minus 1, sir.
Yes, I minus 1. 2 power I minus 1. 2 power I minus 1. And 2 power I minus 1. And hence it is proved that the number of nodes in a particular level is nothing but 2 power I minus 1. That means 2 power level minus 1. So if I simply asked you how many nodes will be there at level 3, then you have to say 2 power level minus 1, that is 2 power 2, which is nothing but immediately 4. So without seeing using this mathematical formula, you can get down that there will be 4 nodes at max in a particular level. Did you understand? Any doubts in this?
Sir,
Yeah,
is this
tell me.
formula work out for every tree, sir?
That's what I'm saying. It is not for every tree, but if you consider all nodes are full and it is called full binary tree, then if somebody asks you how many nodes will be there, how many maximum number of nodes will be there at level 5, the formula works for you. But if you go for a normal complete binary tree where all the nodes are not filled, and there you have to traverse to find out how many nodes are there at that level. But you are talking about the maximum number of nodes that can be fit in a particular level. If I ask you 5, so you will say 2 power 5 minus 1, it is nothing but 2 power 4. There will be 16 nodes at max, not more than 16. But you can be having at a level 0 to 2 power I minus 1. So you can say at a particular level, max nodes will be 2 power I minus 1. That means you will have 0 to 2 power I minus 1 nodes. I'm not saying up to 0 to 2 power I minus 1 nodes. Did you understand? Have I clarified your doubt?
Yes, sir, got it, sir.
Okay, fine. Now, the other condition is the maximum number of nodes in a binary tree of depth k. So it is asking the maximum number of nodes in a binary tree of depth k. The number spelling is wrong anyway. Let us see. What is the depth of the tree here? What is k value?
4, sir.
Yes, 4. Because the depth of the tree is nothing but the height of the tree also. So 1, 2, 3, 4. So k will be 4. Now it is asking us how many nodes will be there at max in a k level. So our k is 4. Now count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10,
15, sir.
13, 14, 15. Right? 15 are there. So how do you get 15? Maybe if 2 power 4 is equal to 16, minus 1 will be 15. So you can say the 2 power k minus 1. This is proven, right? Even if you say if k is 3, let us test with other things. If k is equal to 3, only these many nodes are there. How many are there? 1, 2, 3, 4, 5, 6, 7. Now if you consider what is 2 power k, 2 power 3 minus 1, it is nothing but 8 minus 1 is equal to 7. So it's fine, hence proved. So finalize it. For finalization, I will say at a level, the max nodes will be 2 power I minus 1. At a tree of level, sorry, of depth k, the max nodes of the whole tree will be 2 power k minus 1. See the difference? It's not k minus 1. It is 2 power k minus 1. It is 2 power I minus 1. Okay? So these are the formulas that are discussed in this. Now it is saying that we can also prove by induction. So by increase in level, you can also find out how many nodes are there. So just calculate it. We have a formula, this one, right? You can also calculate like this. Sigma, the level starts with 1 and ends at k. It is said like 2 power I minus 1 is equal to 2 power k minus 1. How do you get it? If, for example, I talk on k is equal to up to 3. Because it is sigma, you need to calculate, right? So 2 power 1 minus 1 plus 2 power 2 minus 1 plus 2 power 3 minus 1. So if you calculate 2 power 0 plus 2 power 1 plus 2 power 2, 1 plus 2 plus 4, so it will be 7. So what is 2 power k minus 1? 2 power 3 minus 1, it is nothing but 7. So 7 is equal to 7. That's what he says the induction is proved. So for every level, if you calculate individually and add them, the total number of nodes will come, which is also equal to 2 power k minus 1. And hence these formulas are very important. So if there is a theoretical exam for you, you have to write with such an explanation, the examiner should be impressed like this. Right? Let's go to the other one. Let us come to the next proof. For any non-empty binary tree, non-empty in the sense there are some nodes in it already. For every non-empty binary tree, any non-empty binary tree, T, if N0 is the number of leaf nodes and N2 is the number of nodes of degree 2, then N0 is equal to N2 plus 1. Okay, let us consider this example. So we have a formula called N0 is equal to N2 plus 1. So let us prove this one. N0 is equal to N2 plus 1. So we can say like this. NL is equal to N with degree 2 plus 1. So degree in the sense this 0 is nothing but the degree. So instead of 0 I kept L, but you can also consider the degree. So the 0 is degree of a node and the 2 is the degree of a node. It's nothing but how many N2s will be there plus 1 is equal to the number of leaf nodes. Okay, let us find out how it will be. If I have a root node, and these are there. Now tell me how many leaf nodes are there in this?
2, sir.
2 leaf nodes, because after this there are no nodes. So we have 2 leaf nodes. How many nodes are there with degree 2?
Only 1, sir.
1. This is with degree 1 and this is 0. So 0 degrees are 2 leaf nodes and 1 degree will be 1 node. So you have 1 node with degree 2. Now let's consider. The node 1, only 1 we have, right? 1 with degree 2 plus 1 is nothing but it will be 2. And this is where you got your 2, right? So if I consider this one, let us say 0. If I have this particular one, now tell me how many leaf nodes are there in this? How many leaf nodes are there in this?
3, sir.
3.
2, sir.
Because we have a degree 0 for this, degree 0 for this, and degree 0 for this. So 3 leaf nodes. How many nodes are there with degree 2?
1, sir. 2, sir.
2, sir.
Because this is having degree 2 and this is having degree 2, because this is connected to this and this. This is also connected to this and this, degree 2. So now you tell me, you have 2 nodes of degree 2. So let us involve in that formula. So we have two nodes of degree 2 plus 1. What will be the answer? 3. Because 2 plus 1, 3. So it is matching with your 3 leaf nodes. Hence the formula is proved. So if anybody asks you in a tree, so this can be workable for any tree, not only full binary tree or complete binary tree or something. Any tree you take, if somebody asks you how many leaf nodes will be there in the tree, you should say the nodes with degree 0, that means the leaf nodes will be always equal to the nodes with degree 2 plus 1. The number of nodes with degree 2 plus 1. Okay, so I will finalize this formula like this. Number of nodes with degree 0 is equal to number of nodes with degree 2 plus 1. This is your formula. That's what the n0 is equal to n2 plus 1 mean. Okay? Right. Now I will ask you. Now tell me how many nodes, leaf nodes are there in this complete binary tree?
4.
How many?
4,
5,
sir.
sir.
5, sir. 5, sir.
5. Because this is 0, this is 0, 0, 0, 0. So 5 leaf nodes are there. Okay, 5 leaf nodes are there. Now tell me how many are there with degree 2?
4,
sir.
sir.
4, sir.
2, 2, 2, 2. So we have 4. So calculate our formula with 4 with degree 2 plus 1 is equal to 5. Right? So it's equal to this one. So that's how. And here, how many leaf nodes are there in this skewed binary tree?
1, sir.
1, sir.
This is the only one with degree 0. Only one. How many leaf nodes are there with degree 2?
0, sir.
0. So it is nothing but 0 of degree 2 plus 1 will be your 1. So 1 leaf node. That's all. Okay. So that's how you can consider the formula. Right. Now I'll tell you the difference between a complete binary tree and a full binary tree. A complete binary tree is part of your full binary tree. I think you can see here like A, B, C, D, E, F, G, H, I are all matching. So a complete binary tree is part of your full binary tree. That antavarku okay, fine, that's fine. Now, what is the difference between full binary tree and complete binary tree? Now you have to say that if you want to say any tree is, just a second, I will open a new book. I have 20 boards used already, and hence it is requesting me to use a new one. Okay, right. Yeah. if you need to talk about a full binary tree, can you tell me how, with what formulas, how do you prove that a tree is full binary tree? Any guess from your side?
Sir, the last but one level, in the last but one level node has two
No, I'm
subnodes, sir.
talking about full binary tree. Full binary tree, this one.
Every node should has a degree of 2, sir.
Yeah, every node will have a degree of 2. Not, you cannot say every node will have a degree of 2 because the degree is also on. Okay, you are saying every node with a degree of 2 and it has the maximum leaf nodes. Okay, that's also fine. The other case we can also say is that a tree will be full binary tree if it can satisfy the number of nodes equal to 2 power k minus 1, and in every level the number of nodes will be 2 power I minus 1. Just now we have discussed it, right? Because it is covering the max. It is covering the max. You see, our formula works: 2 power I minus 1 nodes, 2 power I minus 1 nodes, 2 power I minus 1 nodes. The whole nodes will be 2 power k minus 1. So it is satisfying the conditions. Coming to complete binary tree, it is part of your full binary tree, but a complete binary tree is slightly different. If you have a node, like for example 5, you have incoming 6, you should always keep it on the left position. Next 7, keep it on the right position. Again 8, keep it on the left position. Next 9, keep it on the right position. Next 10, keep it again on the left of your right. Next 11, keep it on the right of your right. See how I am filling up. Can you tell me? See the pattern, how I am filling. So this is
Left,
a,
right.
yeah, it is a complete binary tree. Remember, a complete binary tree is a tree where the new nodes will be filled with importance from left to right in the same level. So you will start here and end up here. Again, you will start here and end up here. Again, you will start here and end up here. Like this. You see, here also you start here and end up here. This is the root. First of all, for any node, you have to fill up its left node. If it is null, nothing is connected. After that, it has to go to the right. If both left and right are full, then fill. Then you have to check for left and connect to the left, and then right. Go to the right side, that is 7. Connect to the left and right. Now, this is an amazing question in Amazon. So during training, one of the student has asked it, and we have solved it. So the question is like this: how can I insert an element with big O of 1 complexity? The question is like this. Now if I'm having 13, where should I connect to? Anybody can tell me?
After
8, sir.
the right side of 9.
What is that? Right side of
Right
8,
side of 8, left, right side of 8, sir.
8. So because this is now empty, so always remember what are the things that we need to connect. What are the things that are still free for connection? The first one is 8. So after you connect with this, 13, if I am having incoming 14, how should the computer know that the next connection should be on the left side of 9? So this is the question. So this is big O of 1 complexity. Anyway, don't worry, I will discuss this one also with you. If you have any idea from your side, you can come out. And the hint is you can use the data structures that you have used until now. Like you can either go for stacks, queues, or linked list, whatever you want. One of the data structure will help you to identify what is the next connection that we can connect simply with big O of 1 complexity. Why I'm saying big O of 1 complexity, I'm not traversing from 5, 6, 8, see whether 12 is empty or 13 is empty, come back to 6, 9. This will take n complexity, and sometimes more than n also, because we have to revisit the nodes that are there already. To get to 9, if for example I am coming in this way 5, 6, 8, 12, I don't know that if I connect to 12 it's wrong. So 5, 6, 8, 12, come to 8, 13, no, 6, 9, and then I have to connect it. See how many nodes I am traversing here. I am coming in this path, right? So it takes n complexity, and he don't want n complexity. He wants O of 1 complexity. It's easy if you use one of the data structure that you have used. Keep the nodes in the data structure and you can find out. That's how you can do it. Okay?
Sir, double linked list.
You try out. You try out that one. So you can take some time and try out after we discuss the binary search tree also. Okay? So this is the challenge that we face in complete binary tree, to keep the nodes in a right position. Now after this, we will now discuss on the binary search tree. It's very easy. After discussing binary search tree, we will implement this using Python. Okay, we will do some problems on board and implement it using Python. After that, binary search trees, then we will come to this complete binary tree and implement it. Then you will have an idea about how to implement that. Okay, so keep it in your mind for some time. After we finish binary search tree, then you can come back to this. Now, binary search tree. Until now, we have discussed on something called binary tree. Now we are going for binary search tree. How the binary search tree will be represented. For example, I have a list of numbers like this: 50, 25, 75, 65, 15, 30, 18, 85. Now I want to insert every element in a tree as a node. Now what is the first element here for us in the list?
50.
50. So first of all, you will design a tree with a root 50. What is the next element?
25.
25. Now you might ask me a doubt, sir, should I insert on the left side or right side? Or do we follow the principles of keeping all these elements as complete binary tree? No, I'm not talking about binary tree. I'm talking about binary search tree. The rule is, if the incoming element is less than, there are no twin values also. Our assumption in a tree is that every value is unique. So if the incoming element is less than the root element, then you insert it on the left side or go left. So place left or go left. So I will just rub it off and write it again. If the incoming element is less than the root element, place left or go left. Remember these points. Okay. If the incoming element is greater than root element, place right or go right. Okay. Now tell me, where should I keep 25 now? Left or right?
Left side, sir.
Left side.
Left side, sir.
So according to the rule, it is on the left side, 25. Finished. Now 75,
Right side.
right side. So until that, okay. Now come to 65. Is it place left or go left? Or place right or go right? Tell me. Difference
Right
between,
side, sir.
because 65 is greater than 50, you have to, oh, sorry, answer. You have to go right. It's not place right. Why I'm not saying it is place right? Can anybody tell me?
Because already in right there's 75. Sir.
Yes, 75 is already placed in the right side. So go right. So that means Now your 65 has to come here. When it comes here, now this one will become root, because now this is the root of another subtree. This is the whole tree and this is the root of the whole tree. When you go inside it, it is the root of another subtree. So this is where the recursion comes in. Now 65 is less than 75. Should I place left or go left?
Place left, sir.
Place left. So place left will work because the place is empty. You can place that one left side because 65 is less than 75. Now the next thing, 15. Now tell me, how do you do that?
Go left, sir, and
left.
place it in the left, sir.
Yes, it is. If you consider 15 with this root, it is less than 50, and hence again 15 will be moved to 25. So this time the root will be 25, and 15 is less than 25, and hence you place 15 on the left side. 30.
Again, we'll go left
Go left, sir.
Go left.
and place it
Place
in
right.
the right, sir.
Okay. So you place it here. 18.
Go left, sir.
Go left.
Again, we'll go left, sir.
Go left.
And again, we'll place it
right.
in right, sir.
Right. That's correct. 18. 85.
We'll go right, sir,
Right.
and place it right, sir.
Place it right. Okay. 85. So whenever I say go left, it is using a recursion. That's what you need to understand. Whenever I say go left or go right, it is using recursion. Whenever I say place left and place right, so that address of the new node will be placed in the left address or the right address. And this is how your binary search tree will be conducted. Okay, this is how the insertion will take place. It's not like the left or right, it should follow the condition. If the value is less than the node which we are trying to insert with, then you have to go or place left. If the value is greater than the root or the node in which we want to connect to, then go right or place right. This is the simple formula that you have to follow for the BST. And you take any numbers and verify whether it will be correct or not. So I will give you a few numbers like this: 10, 16, 100, 99, 25, 62. Now, first of all, do it. Then when I do it, then you verify it. So these are the elements. Construct a binary search tree now. All of you should work it. People who have the highest grasping power will already understand it. There is no need for them to practice. I am asking for the people who are average understanding to practice this. Finished? I think it will be easy. Now tell me, what is the first thing I need to put?
10, sir.
10, sir.
Next, 16.
Right side, sir.
Right side of 10, sir.
Yeah.
Right side of 10.
Right. 16. 100.
Right side of
16,
16, sir.
Yes, place right. 99.
Left side of
900, sir.
Go right, place left. 99. 25.
left side of 99, sir.
Yes, go right, go left and place left. 25. 62.
Right side
Right
of
side of 99, sir.
no, sir.
Right side of 25, sir.
Right side of 25, sir.
Right side of 25. 62. So your shape is like this: 10, 16, 100, 99, 25, and 62. This is what your shape comes. This is the binary tree. Binary search tree, and satisfying the conditions of the binary tree also, because the maximum degree is 2, the minimum degree is 0. In between, you can also have 1. So binary search tree is part of your binary tree, but why the difference comes is the way you insert the nodes into it. Now let's do the program for this using Python tutor. Okay, right. Let's first construct the concept of a binary search tree node. I want the node concept. Tell me how the node should be, because we have left and right. Can you tell me now? I will have a node. How many compartments should be there so that the left and right should be there?
3, sir.
3, sir.
3, sir.
1, 2, 3. What is the left compartment indicating?
Left
Left side, sir.
address.
Address. Right compartment indicating
Right.
right address and data. Now we will construct a small concept. So we have the imagination of the concept, right? Now we will construct that one. Class node. Okay, this is our node concept. Tell me, how do I do it? How do you initialize a object for this node concept?
Definite, sir.
Yes, definition init with a constructor I am initializing. So either you use a constructor or not, you wish, but it's probably better for us to directly use constructor to initiate. The self anyway is always necessary. Next one,
It has a value, a left position and a right position.
we will
2
say,
values.
so always for a node, it's always like left and right will be none, right? So there is no need for me to pass those nuns. I will initialize directly here. So what I will do now is self dot data is equal to, so these are instance variables, these are not even class variables. See, every time refer to what is class variable, instance variables and local variables. Okay, self dot data, if I write data is equal to something, I can write something like this to initialize. What we say, RA is equal to none and LA is equal to none. Is it fine? Is it
Yes,
okay?
sir.
What are LA?
Class variables, sir.
Class variables. So all the nodes initialized with some data will by default have both nuns. Okay, I will give it like this. If I don't have class variables, I can just copy it and paste it here, but I need to give self. So these are called instance variables. Of course, class variables are also instance variables, but class variables don't need to get initialized every time. They will be by default for every object. Here we are trying to initialize. Whether it is class variable or instance variable, all should be mentioned with self because they are all part of instance. So what I will do now, I will go for class variables because I want it to be common to all. Okay, data might be different and hence I am making them as instance variable. Right, of course, finished. This is the concept of the class node. I will have definition main. I will write the code now. Until then, if, how do you do? How do you write this? Tell
Uh,
me.
underscore
M
underscore main
equals to main.
Underscore equal to double equal
double
to
equals to first double
main.
quotes main
Yeah. Next we call the main
main
function.
function.
Yes. Now create our first root. So no need of any income or something, input or something. We will directly write the data. So now create the first root.
Root is equals to none comma value comma none. Means value means something.
Why should we use none? None is already class variable. By default, it will be node of what you have to give. How many
Node
parameters?
of 5 or
Data.
Yeah, node of something like 50. The same thing that we will look into. Okay, earlier example that will be fine to construct a beautiful binary search tree. And so we have constructed a node of 50. Let's see how it will work. So we have our class concept and the root is being constructed with data. Okay, I think it is not showing in it. Of course, it will be by default none, but I want it to be shown perfectly. So what I will do, conceptually, okay, for visual representation, it is not showing it. So I will just come back, revert back to the instance variables only. So I will go for this. Self.ra is equal to and self.la. Now I think it will be fine. Now in memory both are equal, but here the representation is different. That's why I'm going for this one to make you visualize what is happening in it. Yeah. And I think you can understand that the root has been created in main with both our nuns and data. Now, okay, fine. Now we have to create the next one. The next element is what? What is the next element that we got? So now we got your root. So my root is prepared now. Okay, my root is prepared with 50. Both are none. It is having an address 6101. Okay, fine. What is the next thing? Now I want to insert another thing. Same like your insert in your linked list, but the slight difference comes here. Insert. What is that insert? What we need to do? Same like linked list, you tell me, what should I keep here in the insert function?
Root comma value, sir.
Yes, root comma the value. What is the other value in our example that we have taken? 25. Okay, let's go for 25. Right. Insert 25. Now we need to write the insert function. Definition insert root comma data, the new data. What is the first thing that you need to do like linked list?
We need to create a new node, sir.
Yes, we need to create a new node. So first of all, we create a new node in some random location. I am keeping it correct because it will be in random location, but for us, if I want a diagram to be perfect, I am keeping it like this with none, and we should get 25 here, and it should be placed in some memory location 7010 something. Okay, now we need to connect it so that the LA and RA should be having the addresses, right? The LA should be having address 7010. First of all, let me create a new node. New node is equal to, tell me,
Node of
of data.
data, sir.
Okay, so it will be created with both nuns. Now tell me the condition. First, we only want to go to not go right or go left. We want to place left and place right. For that, you tell me the condition.
We need to check whether the data is greater than the root value or not, sir.
Tell me condition. If root dot data is less than, okay, let me go it in
Greater
another.
than
New node dot data is less than root dot data. If new node's data that is 25 is less than the root dot data that is 50, then tell me what to do.
root dot LA is equals to new
Yes,
node.
root dot LA is equal to
New node.
new node. So what happens in this case? It will rub off that none and include that 70
7010.
as the address and get it connected. So connecting to the whole node, it's not like left or right or something. Connecting to the whole node, this means. Okay. Now we had a connection, perfect connection. Now let us see, visualize it, whether my board is.
Sir, I think in the eighth line we have indentation error.
What is that, Amma?
Sir, I think in the eighth line we have to give a tab, sir.
We have to give it tab. No. I'm not including that insert in the class. I'm making it outside. In class, I'm only creating the node. That's all. No functions in the class. Did you understand? The
Yes, sir.
function is independent, which is using the root. Like we have discussed it, right? We can use the classes even in the outside function. So I'm using like that. So I'm creating the node first. Okay. The data with both LA and RA none. Next insert 25. In line 8, it will come and a new node will be created now. So you can see the new node has been created. You can see the two arrows, root and new node. And after that, it checks the condition in the level and it satisfies. Hence, the root's LA will be now connected to the new node. You see. Yes, I think you understand that red arrow. The LA of root is now connected to the node 25. Now, the next thing that we need to connect is 75. Let us see how it will be done. Insert root 75. Now, the same thing happens, it comes to the 9th line and creates a new node. Hence, we will also draw it. A new node will be created. Okay. And we have 75 here. And some other like 8162 some address is there, and we need to connect to the right side because our condition is 75 greater than 50. Now tell me, what should I do now after creating new node? Because it is not satisfying the condition in the 11th line. Can you tell me another condition to place right?
So can we keep an else and we can do it now, sir?
You can keep else, but I prefer to write the conditions because they are very clear so that people can know, because you are in a learning stage.
New node is greater than
no
root dot data.
dot data.
Okay, right. This is easy until now. So you will have root dot, what is that?
RA, sir.
Right, is equal to new node. So in this case, what will happen is that you will have this one rubbed and 8162 will be included, and this is connected to this. Now we formed a beautiful binary search tree until now. Let us see how it works in our Python tutor also. Okay, so like this. So it is connected. Next we have 75. A new node called 75 will be created. You can see this red arrow, and then it is checking the condition, and the 14th line condition is satisfying, and hence it goes in and connects to the right. You can see the red arrow connecting to the right side from the root. So your LA is connecting to 25 and RA is connecting to 75. See, this visualization never gives a tree like how we are drawing it on board. Some random locations it will present and connect it. We only need to follow the connections. So RA is connecting to the address of node 75, LA is connecting to the address of node 25. Until now, everything is fine. Beautiful and happy life. Now comes the tragedy. How the tragedy comes? In the form of,
Going to left and going to right, sir.
yes. Now, until now, we are only going to place left and place right. Now we have a new one called go right. Now, let us see how we can do that, but we will take a short break and go for the next period, end of this. Okay, so Taruvai Bhagam Vachevaram. You have to keep the suspense there. And now we will try out using something called recursion in the later period. Okay, any doubts until now?
No, sir.
Okay, then fine. Bye bye.